So, welcome to the last session of this group theory LTM series. Today, as the agenda shown on the screen, we'll be doing commutative diagrams, universal theorems, and free groups. And well, the intuition about uh, this thing, what is it? The homology will be essentially a topic that is used in contemporary group theory so that it gives you an intuition onto how exactly group theory is nowadays used in its most general essence, rather than being like, okay, just because group theory has a application of some sort of definition in every field. Example, we use vector spaces, as in we use Rn in many of our courses like quantum mechanics and what is it called? Rather, CN, complex spacer. So we use the definition of CN everywhere, but it's not exactly the definition of vector spaces that we use, but particularly the properties of CN itself. But homology I speak of because in homology we particularly use the properties of groups, especially to derive uh, you know theorems regarding these big objects called uh, or even simple concepts like showing how R2 and R3 are not homomorphic. Um, Basically things like that. And there are other things like knot theory and even this thing, data science. Nowadays we have topological data science where we essentially consider our data to be existing on some sort of a nice space called a topological manifold and then see the property of that space using homologies. So we'll go to commutative diagrams first. So a commutative diagram is a very general concept in abstract algebra. Particularly, it's just a graph in the most general sense with nodes and edges such that if you fix a starting and an endpoint, whatever path you may choose to go through, let's say this is the starting and this is the endpoint, any path you choose will lead to the same answer. So an example that is the simplest one to follow is, let's suppose you have a map from G to a group H, which is a group homomorphism. Then if you go G mod kernel phi, going through this route is the same as going this route. So essentially phi of G is equal to this projection map, taking the projection map and then taking this map that is defined afterwards. So it's equal to phi composition phi of G. So essentially this is a commutative diagram. If I make a general one, a commutative diagram might look like this. K, L, M. It need not have only one endpoint. Here you have only one endpoint, but you might have multiple endpoints like this. So things like these are possible. So example, to get here, you can go this way, or this way. Point is to say that this diagram is commutative You need all of them to give the same answer, and you can't be like, okay, going through one of these ways differ from the other. Yeah, that's what a commutative diagram is. So, any doubts regarding this, Oishik?
I'm still not. I could not grasp it properly. You would be possible
Okay,
to
okay.
explain this?
Yeah, of course. So, essentially, if you take A to be a group, B to be another group, and C, and let's suppose you have a D and E. Let's suppose these arrows kind of join them together. Let's say this is also. This diagram is said to be commutative. This diagram is defined to be commutative. If you start from A, let's say, this is our starting point, and let's say this is our ending. Any path you choose from here A to B to C, then E, A to D to E, and A to B to E. All of these give you the same endpoint. As in, let's suppose this map is K, K1, this is K2, this is K3, K4, K5, K6. These are maps. Then K3 composition, K2 composition, K1. This denotes this path. This should be equal to K4 composition, K1, which is A to B to E, this path. And this should also be equal to K5 composition, sorry, K6 composition, K5, which is this path. So essentially, whatever path you take, it should give you the same value for a given input. So the input will always be from A, and the output will be on will be from E. You understand now?
So, if we just specify the input, we will know what the output is, irrespective of the path we take.
Exactly. The output does not depend on the path we take.
Okay. Yeah.
Yeah. So that is what a commutative a diagram is. Now you might ask, isn't this always true? Not exactly. So there are diagrams which are not commutative. So in a set language, because if I talk about groups, I have to specifically talk what group. But if I had to tell about sets, so right now talked about groups here, but these need not be groups. I mean, I never use group property here. So in algebra, a diagram is said to be commutative if the output does not depend on path. That's all. So in this case, let's say if we take D to E, actually, why not just direct do it? Just take this and then take this. So let's say if you have input 1, let's say 1 goes to 2, which belongs to B, but 2 is mapped to 3. But this map, 5, 5 of 1 actually gives you 4. Then this diagram is not commutative. Even though the map is well defined. The map from A to E is well defined. The map from B to E is also well defined. But the fact is the composition is not well defined. In the sense, these two maps are not the same. That is why they differ. If you let's say need another example, take Z. Z goes to let's say Z again, and then again it goes to Z, and then there is a map direct. So this map, let's say, goes to 2Z. So it's 2 times. And then it, let's say, divides by 2. So this is essentially an identity map, right? This whole thing is the same as saying it's identity map. It's just 1 times the value. But if I define this to be 3 times the value, These two maps are not the same. This and this are different. If you take input one here, going through this path gives you the output one only. But if you go through this path, you get output to be three. And hence, this is not a commutative diagram. But what is a commutative diagram is the first isomorphism theorem. That is, given a group G, you define a map, you have a given a map phi, then you have the projection map G mod kernel of phi, and then there exists a unique map capital phi that goes from here to here, which is exactly phi of G kernel phi. This is coset notation. This equals phi of G. Phi root, that's the wrong notation. So this is a commutative diagram because of this thing. Because this is essentially equal to phi composed with the projection map on G. Did you understand?
Just to confirm, once the kernel was the operation where G times that we gave the identity one. I just forgot what the kernel set was.
So the kernel was essentially defined as set of all elements such that phi of, let's say, if G belongs to kernel, phi of G equals identity in H. That's all.
Yeah. So I mean, if the in the commutative diagram, so suppose I start from Z and I end in Z through one path, and to the other path also I end in Z. But
Hmm.
so, but suppose to the first path, 1 in Z maps to 3, and to the other path, 1 maps to 2. So, like I can always define that. So, suppose one path is first plus 1, then plus 1, and the second path is just a single plus 1. So, all both are giving me Z, but they are different because the final, because from 1 I get 3 in one direction, 2 in another direction. So,
Then that does not form a commutative diagram.
okay,
Here
okay,
we have the functional outputs to be the same, regardless of the path you take.
okay.
Yeah. So essentially, yeah, you commutative implies it is path independent. You can't put two different outputs. I mean, in some cases, it might seem like, so in some cases, you might get two different outputs and you might be like, oh, because of the fact that there is another node now, I might say it's a commutative diagram, but in those cases, again, there will be a contradiction somewhere. It is for sure that you can't have a commutative diagram if you have different outputs. But regardless of that, there is another thing. Now you might say, what exactly is the use of commutative diagrams? Commutative diagrams literally give you big theorems. So, in case of, let's say, this thing, as we will further go, it's called groups. Using free groups, essentially, you can form infinite chain of nodes. Let's say A1 to A2 to A3 to like these chains of maps, and then you can map it to other chains B1, B2, B3. Dot, 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 dot. So you might have this kind of diagram, and you might not be sure exactly what the properties are. There exist theorems that can tell you what exactly these properties are, given you know things about, let's say, these two guys only. And well, maybe let's say if there is another map that goes diagonally, then you can talk about what exactly is the properties of chains derived from these. So having commutative diagrams actually makes lives more easier in algebra because to state big theorems in form of maps is a very tedious task. You might have infinitely many number of these maps. So drawing commutative diagram essentially takes care of you defining, maps. You don't have to define them specifically. We don't. So example, if I write this, I don't define what this map is, what this map is, and what this map is. I just write this. But in case you might say, okay, what if I want to write something like there exists a map? The notation for that is, so this is usually not a notation everyone uses, but it's a notation someone uses if they want to tell something. For example, if let's say this is given, this is a given map, and this is also a given map. I want to say there exists a map between B and C. I just write it as a dotted map. This dotted map implies there exists a map like this. But this is not the only case where you can say there exists a map. So something like this might happen where you know the path A, B, C, but you want to make a path from A to C direct. So what was the thing here? You had a map from A to C, and then you needed this derived map. Now you don't want a derived map. Now you want an original map from A to C, a direct map. These kind of maps are called the lifts, and lifts are very important in math because, as you think, if you might think of lifts as, let's say, taking something and projecting it up, in the sense you have, let's say, a base space X, and you have a diagram of a triangle given, but you want to see its orientation actually in space. You can lift it up and maybe it looks like a slanted triangle of some sort, right? So this is exactly what lift is. So in this case, our base space is R2 and our lift space is R3. So this is exactly what this is doing. You have a base space A, you have a lift space C. You know how a map works from here to here. You want a map from A to C. So lift a triangle into a triangle in R3 with some orientation. So these lifts are very common thing in math, and then you might say, okay, okay, what the commutative diagrams regarding that. So that is what commutative diagrams are. Now we'll come to what universal theorems
I can understand the lift which you mentioned from the example that you gave, the triangle.
are. Ah, okay, okay, okay. So let us suppose you have R2 and you have a triangle in R2. And let's suppose it is mapped to a space B, which is, let's say, a plane in R3. So this is a plane in R3. So you have R2 triangle. This is mapped to a plane in R3. This plane is defined to be B, but this is a space again. So, and then I map it to R3 itself, as in like it's an identity map in that sense. It's an identity map from B to R3. So I just put it in R3. So essentially, if you had to see it visually, this is like taking a triangle on the XY plane, lifting it up into R3. This is how it looks like. You understand that?
Yes,
So essentially, this is why this is called a lift map. Now, of course, I am kind of simplifying it here because not all lifts always look like this. In fact, lift in general is a very abstract map, really. But the point of the matter is the motivation for a lift map comes from this exact reason that you have a map on this space, then you get it to another space B, and then you put it in R3. Now, again, when I say B is embedded in R3, this is what embedding is. It's again not necessary. Actually, B might be a separate space itself, and then it comes to R3. So, in that sense, I could say the triangle is first embedded into R4 and then projected into R3. This is also a case that might be possible. But in that case, telling what a lift is in this analogy is very hard to do. And that is why I did not go there. And that is why this is the most simplest scenario of how you could define a lift. Nonetheless, if that
yes.
is Yeah.
Eventually, both a lift and a link both are basically mappings.
What?
Eventually, both a lift like A to C and a link like
Uh,
B to C defined. Both are. I mean, is there a difference between the two or
essentially, point is this you can derive given this, right? If you have this and this, you can derive this directly. What happens in this case is you might have to define what this map is. Here, defining is not a problem. There is one unique way to define a map. Here, turns out you actually might have a lot of ways to define what this map is, and you have to specifically take them. Now, how I mean this is you have to get into some examples that are in case of topology. So, example, if you have A to B defines, so if you take a point A, let's say it gets mapped to B, but not uniquely, in the sense there might be other points that map to this point as well. And then you map it to C. Now the problem is how do you take all of these points and map it to C, right? That is a very hard idea to go through. So that is why what you do is you rather first fix one point and then define this map. Do you understand?
kind of? I think.
Yeah. So essentially, point is that I won't go into the details of the map, but the point is defining what this map is different in both of these scenarios. Here the map is easier to find. Here the map you have to first construct in an artificial way and then see if it follows the rules of commutativity or not. So essentially going through this path is the same as this. This condition you have to check. And well, turns out in many cases, in fact, the lift you get is unique as well. Of course, here also, here the uniqueness is always implied, guaranteed, in fact, because commutative diagrams are guaranteed to give you this unique path. Here, the uniqueness is not guaranteed because you want a direct path. Here, it's not a direct path. You are going from A to B, and then this link is not starting with A. But here, this is starting from A, and that is why it becomes a problem. But nonetheless, yeah, that is what differentiates this case from this case. It takes a while to actually get an intuition about why exactly these two are different. In my first instance of seeing this, at first I wasn't exactly able to differentiate because I was like, wait, they both seem to be same triangles. I mean, they form the same triangular diagrams. But then afterwards, I got a sense of okay, why exactly are different? They are different. One is this problem is harder usually, and well, the second is this has to be defined sometimes unnaturally. Well, this comes naturally because this follows from some sort of projection or something. This looks like a projection, right? You take B and then you project it into C. This looks like reverse of a projection. You have been given a projection, but you have to put it into a bigger space. That is why this becomes a harder problem. You understand?
Yeah.
Yeah. So, anyways, coming to universal theorems, these are called universal theorems because they essentially give you a sense of how uh, how something can be defined without actually defining it. How I mean that is, so this is how we define what are called free groups. So technically, I should have put universal theorem and free groups. So this can be taken in two ways, by the way, as a definition or a theorem, depending on what you do. So this essentially says, given a group V or given a set A, and a map phi from A to, let's say, a group G, the group H, there exists a unique group. Okay, no. There exists a unique group F, obviously up to isomorphism, such that the following diagram is commutative. So A to H is given by a map phi. Then you have, so there exists a unique group F such that this is true. So now you see what the problem here is. This is not a problem about finding a link or a link. There are two maps that are unknown, this map and this map. But I can guarantee that there exists a group such that this diagram is commutative. That is, there exists this map and this map. So point is, this is a group homomorphism, and this is supposed to be some kind of projection of A into F. So now you might say, how can you always guarantee this? So that is why, so this group F is called, this F is called a free group. And also there is another condition, given a set A and any map phi to any group X. So this F is unique for any X and any phi. So do you understand what I said, or was it confusing? So essentially what is fixed here is only A. That's all. Phi can change, H can change. But the output is F that is unique.
And A need not be a group here because it's a defined
Yeah,
A set.
A is just a set. So in notational language, it is written as f of a, but I don't write it because f of a we will define particularly how it looks like. So there is a canonical definition, or in a sense, natural definition of what f of a looks like. And then you can, of course, create isomorphism of f of a into any other group you want. But the point is, there is a canonical way of defining what f of a is. So some books and some authors define this. So they take this as a definition and say that, okay, f is a free group. But then other authors first define f of a and then write this as a theorem. And that's called universal theorem. And it's universal because this works for any phi and any x. The only thing that is fixed here is a, and then you get the output as uniquely as f. That is why it is called universal theorem. So now, instead of going through the first route, that is defining this as the free group and then showing that such a group exists. So then this will be again a theorem. This would be a theorem that there exists such a group, and then you have to prove that such a group exists. We will first define what f of a is, and then leave this as a theorem that will be there, because proving this theorem actually is not exactly that hard really. But so there are two ways to prove it. Okay, there is one intuitive way where you will be like, okay, I can find the kernel directly, and we'll be like, yeah, the kernel is obvious, so I don't need to prove exactly everything here. And then there is another way where you specifically go through the process of showing that this is the only group possible, that uniqueness. And that uniqueness part is what becomes non-trivial. And that is why, so I'll give you a proof about the uniqueness part separately. So here only, in fact. So let's suppose there are two groups, F1 and F2, right? Which are three
Just
groups.
one more question in the definition.
Ha ha ha, sure.
You said you wrote up to isomorphism, and what does that mean? You
Up
said
to
in the
isomorphism means up to isomorphism means if let's say A to F1 X, if let's say this property holds for F1 and F2, then this would imply F1 is isomorphic to F. This is what it means.
okay, okay,
Yeah. So essentially, now proving this part is in fact easy because you can just write. So you can take H to be F2. So this is commutative, and then you can take F2 here and F1 here. So both of these are commutative diagrams, and hence, with just a little bit of calculation, in fact, working with the symbols, essentially being like, okay, take A to be A1, A2, dot, 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 maybe. And then just do some calculations, and you'll be seeing that, okay, you have a map from F1 to F2, and then again from F2 to F1. So this becomes an identity. And if you prove that, that implies F1 is isomorphic to F2. So it's as simple as that. So the uniqueness part is in fact not exactly a problem if you go by first defining what f of a is. It becomes a problem if only you have to go through first taking this as the definition of what a free group is and then defining what the free group is. So I'll tell you what free group is now. By the way, you understood it here, right?
yeah,
Okay. So to construct a free group, first we consider words on A. So what exactly are words? So before even words, take A to be for simplicity purpose A1, A2. Now, by the way, it can be uncountable set as well. It need not be countable like we have taken here. So it can be any set per se. But just for simplicity, I have taken A to be like this. The definition can be taken for any uncountables. So if you take A to be this, you define A inverse to be just sets of symbol, by the way. This is in no way, so this is not math in that sense. This is just symbols. You define it as A1 inverse, A2 inverse, blah, 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 blah. This has no meaning. It's just a set. This is just a notation. And in math itself, so in the language of group theory, these are called symbols. And then you take E, also a symbol. Now what do you do? Now you define a set named C of A, which is all the permutations, finite permutations of elements in A union A inverse union E with repetitions, with possibly repetitions. I mean, repetition is not necessary, but possibly repetitions. Did you understand?
but in sets we don't allow repetition. So
No, this is not a set. This is finite permutations. This is not a set, right? Permutation is essentially creating another symbol like this. A1, A2, A3 inverse, A3, A3, A1, A1. So this is not a set. This is a word in some sense. E, E, E. That's it. This is just a symbol. Concatenation of words.
Okay, and A inverse you said was symbols, so are symbols also sets?
No, a symbol is not a set. This is not a set, right? If it was a set, I will put commas. And then you are correct. I can't repeat E again and again. So this is not a set. This is concatenation of letters. Like in English, you can write this, right? Possible.
Yeah.
This is not a set. This is a word. In fact, the name for these symbols are words. This is a word. In language of free groups, we actually call this a word. Actually, because we are not yet in the group itself, we call it a pre-word. It's not a word yet, but this is what a pre-word is. It's just as symbols like this. And then we actually get into the group. So we call C of a group after defining it under the equivalence class. Now we consider equivalence relation. We so a word, let's say I denote one word as uh, M. A word M. So this is a concatenation of letters. So A1, A3, A2, A5, something like this. So M1 is related to M2 if either of the following are true. Following are true. They have AI AI inverse pairing or AI inverse AI pairing and rest everything visually looks the same. Two, they have EA or AE and A and rest everything looks the same. So the same thing. You don't understand what this means. So essentially, I consider A1, A2, A2 inverse A3 to be related to A1 E A3, which is related to A1 A2 inverse A3, A2 A3, and this is related to A1 A3. Did you understand?
I'm not sure about the two rules that you mentioned.
Essentially, that is why I'm saying. So this is what the rules translate to. You don't care about these kinds of pairings, and you don't care about E. You see, this is related to nothing being there. So essentially, the rules in the group you want, AI inverse should be equal to E. This is what you want, right? So you essentially, what you want, you put it as an equivalence clause. You say that, okay, these two are related.
So
You
basically,
understand now?
like basically between two words, I mean, in two words, suppose there are two symbols I'm considering here, which is A1, A3, and in
Hmm.
between them, there are varying amount numbers of A2, A2, A2 inverse, A2 inverse, A2, those kinds of pairings. So those will, I will neglect them.
Yeah, essentially. So we will neglect. So we can't directly put the neglecting factor right now. Right? So what we do is first we make the equivalence relation. So proving that this is an equivalence relation is an easy thing. You can do it yourself. But you take an equivalence relation, prove it, and then you take a equivalence class. So you partition the set using equivalence class, and then you have these properties in the image in the image set. Right now it's a set. So in the image set we have these properties. So a1, a2 is equal to a1, a3 inverse a3, a2, which is equal to a1, a3, a3 inverse a2. Do you understand?
Yeah.
Yeah. But in this case, now if we take our operation to be just concatenation. So now our operation becomes concatenation. So you can take a1, a2 as one word, operate it with a2 inverse a4, a5 maybe. Then this will give you a1, a4, a5. But in general, a1, a2 concatenation with a3, a4, a5, this will give you a1, a2, a3, a4, a5. So this is my operation. Essentially, this operation is called concatenation. Now, whatever whatever elements of the image are, these are called words. These were pre-words, and whatever is in the image are called words. Did you understand?
Once more, could you please, I mean, explain the, see, we are defining an operation on which one?
We are defining operation on f of o, where you have these relation, where you have this relation instead of an equivalence relation, where you have this equality now.
I still can't get it. We define C of A from A inverse and E, and after that, how do we get F of A?
So first we defined an equivalence relation on C of A. So C of A was all finite permutations. So you had this kind of a problem, right? You can write E, but never tell if this is equal to E. This was not the case in C of A. So what you did is you did an equivalence relation, you put an equivalence relation, and now you have this relation in f of a. So now the equivalence relation partitions the set, right? And what are the properties of partitioning set? It essentially implies words like pre-words like this are equal in the final set. Our final set is f of a. So in f of a, you can't say that a1, a2 is equal to this or e is in fact equal to e. Things like this.
Okay, so F of A is my equivalence class. Fine.
Yeah, f of A is the set of equivalence classes. So when I
Okay.
say they are equal as equivalence classes. I'm not writing this because this is, I thought it, like essentially when people write it in books and all, they usually don't consider this brackets because they're like, okay, it's clear from the context. So technically speaking, I should write this. But if the context is clear, I will avoid writing these brackets.
And when we are doing the concatenation operation, we are basically doing them on the equivalence classes, like one equivalence class and
Exactly.
the other class.
Exactly. We are actually concatenating the equivalence classes, but In because of the following that A2 inverse A2 A2 inverse the class is the same as E, you can write this as this. So this is a well-defined operation.
Okay, and this definition of C of A, I think initially I was confused, but now I'm clear. Could you please just listen to what my interpretation is to just check if I'm correct or not?
Yeah, yeah, sure.
I mean, I think C of A was you defined that A union A inverse union E. So
Mhm.
I take all the symbols which are present in A, all the symbols present in A inverse and E, and then I mix the ordering of the symbols. So the different orders are different elements in C of A.
Exactly.
Okay, okay.
Yeah.
Yeah, now
Yeah. But CFA wasn't a group. So now we formed a group from that. So essentially now, how can we call this a group? Because you already only have an operation here. Because now things like these follow. A1 inverse is equal to the inverse of A. This you can define like this. Or rather, the definition goes the other way around. So you can define this to be true because you know that, why did I write A2? Yeah. Because you know that A1, A1 inverse is equal to A1 inverse A1 equal to E. You have this relation, hence, by the group law, this is true. Similarly, you can prove other facts like A1, A2 inverse is equal to A2 inverse, A1 inverse. These things are easier to follow. So this is a symbol, this is a symbol, this is a definition. Other things are you can also see is yeah, this is not true. A1, A2 being equal to A2, A1. This is not given to us. We said all unique permutations. So this is a different permutation. This is a different permutation. These need not be equal. So in general, f of a is not a BDM. So you have to keep that in mind. And well, yeah, this is what a free group is. It is essentially the set of all words you can form, and the operation is concatenation. You understand what a free group is?
yeah,
Yeah. So the unique property of free group. Now, essentially, you might be like, okay, this seems very artificial way of defining a group. Point is, it follows this very important theorem. That is why free groups are so important. It is the unique group up to isomorphism, such that if you take any homomorphism, if you have a set A and you have any homomorphism phi to a group H, it follows through this unique group f of a. So f of a, you have a direct inclusion of a to f of a as a symbol, and then you have a unique homomorphism capital phi. So how is capital phi defined? Capital phi is uniquely defined via ai is equal to phi of a. A. Only defining. This is the beauty of it. Only having the definition of what how phi defines on these specific elements gives you a definition for another homomorphism. This is the beautiful, what is it called? Property of it because this phi is uniquely defined now. And this is a homomorphism. This was a set map, but now you have a homomorphism defined. This is the beautiful thing about this universal theorem. Now, I don't think I'll go into the proving part of this universal theorem because Believe me, it's very simple, and you actually can try to think on it and probably come up with a proof in maybe like 2 hours or so if needed, not much. But yeah, the only thing that is necessary is you being clear as to how to get into it. Because if you don't have an understanding of what the theorem says, then it's very hard to get to the bottom of how the proof works. But if you have an understanding of how this works, the construction, proving how this map is unique is very easy. Because you essentially define phi of a word A1, A2, A3, A4, let's say, to be equal to, this is a definition, phi of A1, phi of A2, as simple as that. This is how you define it. So once you have this definition, you have this map uniquely defined. That's all the proof is. I'll let you fill the details of the proof if necessary. But is it clear?
From A to when we are defining the A to F of A, the mapping, previously we used A and A inverse also. And here, where is the, I mean, what we use is the A inverse.
Yeah, yeah. So the map from A to F of A is direct. It's just A goes to A. AI goes to AI. That's all. It's a inclusion map. The map that is has to be found out is this map. You understand?
Not quite, I think.
So essentially, the map from F of A to F of A is direct, right? It's just because elements of A are just AI. AI goes to AI in F of A. AI itself is a word in F of A, right? You can take AIE, which is equal to AI.
Yeah, but then which one is the A inverse?
Yeah, A inverse is in this territory. There is no A inverse in A. A inverse exists here. So now you define, now I get what you mean. So you define phi of AI inverse to be equal to phi of AI and then inverse of that in H. This is how I define phi of AI inverse.
No, like when you initially defined the free group before this, you took
Hmm.
a capital A equals to A1, A2, A3, A4, and then you also took capital A inverse equals to A1 inverse, A2 inverse, A3 inverse, and then you defined C of A from that, and then F of A. So
So remember
and
I said there is no relation between these two guys. There is no relation between these two guys when we were defining A inverse. These were symbols. These had no meaning.
yeah,
Then we gave it a meaning here by defining this equivalence relation. So now we have a relation between A1 and A1 inverse. So these are two independent things. Now we made a relation between them that they are inverses of each other. So till here we had no knowledge of what A inverse is. There exists no information how A inverse is, or it's nonsensical to even think about A inverse when we are here at the level of A. Only after we define what a free group is, we have a notion of what A inverse actually is. It is just another symbol such that A1 inverse gives you, that's it.
okay. So here
So
when
in
we
that,
were yeah,
yeah, continue.
yes. So in that commutative diagram, when we are defining the A to F of A mapping, we do not know yet what the A inverse is.
Exactly. We have no notion of A inverse here. So this
Oh,
mapping does not care about A inverse.
okay.
Yeah. The mapping that cares about A inverse, on the other hand, is this part. Because now we need a homomorphism. And if we need a homomorphism, we need to define what AI inverse is going to give. And that is why we define phi of AI inverse to be actually equal to phi of A and then taking its inverse in H, which is defined. So in the level of this, def- talking about AI inverse is a nonsense because phi is a set map, that's all. But at the level of H, it is true because at the level of H, I can take inverses of elements. H is a group, right?
Yeah.
Yeah. So are you clear with the idea of how I define capital phi?
I think so. Yeah, till now.
Yeah. So this is exactly what free groups are. So essentially, the use of these are well in essentially one of the big use of it. In fact, so this is the largest case use of free groups I've ever seen in math as such is homology. So how do you define homology? So now I won't go into specific topics like the how topologically you define it. So of course you don't actually require homology to you don't actually require topology for the definition of homology, but I will give you the definition of what homology is in context of Rn, real numbers, or well, the real space. So if let's say you have what is it called? Triangles, right? So I define dn, or rather, I define delta n to be a triangle in uh, Rn plus 1, a n dimensional triangle in Rn plus 1. How exactly? So if you consider delta 1 is a triangle in R2 that looks like this. Oh, wait, delta 1. So it's a triangle that looks like this. This is the triangle. If you consider delta 2, I will define it in R3. So like this. It's a two-dimensional triangle. And in R4, it will be a tetrahedron. So essentially, it's a n-dimensional triangle in the positive quadrant of Rn plus 1. Did you get it?
I'm not sure. I mean, how do we define the triangle? Still, I mean,
Yeah. So del- it's defined in the visual way only. Don't so mathematically speaking, it's just the set uh, summation xi, so coordinates such that uh, summation xi is equal to 1 and xi's are greater than or equal to 0. That's it. This is how I define it. So graphically, it looks like this. So delta 1, if you have delta 1, it will be x1 plus x2 equal to 1. So that will be this line. But you want both of them to be positive. So it will be just this part, this horizontal segment. So delta 1 is a line segment.
yes, in delta 2, we take three triangles. I mean,
So
we take
delta 2,
three.
you get what?
Delta 2, we take three lines on the XYZ axis.
But equal to 1, right? So x1 plus x2 plus x3 equal to 1 defines a plane in R3. So it will be all of this plane. And then you restrict it to the first quadrant. So you get this.
But then delta 3, then how do we define it?
So delta 3, again, in the mathematical way, you define it as x1 plus x2 plus x4, x3 plus x4 being equal to 1. So it defines a three-dimensional uh, uh, volume, so a three-dimensional plane. So it's an R3 in R4, but then you restrict it to the first quadrant of R4, and then you get a tetrahedron. So it's a tetrahedron.
Okay.
Yeah. And then again, you can define delta 4, which is in delta 5. So essentially, a delta n is a subset of Rn plus 1. That is a crux of it. Did you get it?
Yeah.
Yeah. Now, of course, there is a natural way to define boundary of delta n as well, right? So, so delta 0 is just a point, by the way. So delta 0 is essentially x1 is equal to 1. So it's just the point 1 on the real line. So now I can define boundary of a delta. So delta 1's boundary, which I'll define it as dou of delta 1. The boundary of delta 1 is essentially 2 points, right? And this point is 0, 1 comma 0, and this point will be 0 comma 1, right?
Yeah.
Similarly, I can define what delta 2's boundary is. This one is going to give me a connected boundary though. You see, delta 2's boundary is going to be this outer. So it is going to give me the actual triangle without the insides. You see that?
Yeah, but why can't I just define the three vertices like 1 0 0 0 1 0 0 0 1?
No, but that's not a boundary, right? That's a vertex. What I want is a boundary of this.
Okay, so the external circumference.
Yeah. So I get a connected boundary. So right now, when I say connected, you don't have to go into the topological definition of how connected works. It's as simple as if I can draw it without lifting my pencil. So similarly, delta 3's boundary will be in fact, so here you see it's a triangle, right? So delta 3 is a tetrahedron. Tetrahedron's boundary is going to be two-dimensional triangles. But how many triangles? So it will be connected, of course. A tetrahedron is connected, so its boundary is going to be connected. But what is the boundary of a tetrahedron? Of course, it again looks like a tetrahedron, but how many triangular faces will it have?
4.
Four. So it will be four triangles. So similarly, you can define what boundary of delta 4 is, what boundary of delta 5 is, and the number of finding the number of how many such boundaries are. It's just a matter of you doing some permutation combination of things. But yeah, that I'll leave up to you. Point is, you can define this function. So this function is well defined. That is a point. So now, if I have a space x, any space x, I can take maps from delta n to x, right? I can take these maps, sigma, true.
Yeah.
Sigma is any map delta n to x. What I do is, I define Cn of x to be equal to the free group generated by all the maps sigma from delta n to x. This is how I define Cn of x. So it's the free group of all the maps from delta n to x. So in some sense, if you have to think about it, it's all the n-dimensional triangles in X. Did you get it?
Once more, you please say this, all the n-dimensional triangles in X, how are we getting?
So taking a map from delta n to X is essentially taking delta n and somehow embedding it in. So let's say X is a space. So it's essentially taking delta n and embedding it in X, right? So if let's say it was delta 2, it is essentially embedding a triangle in X, right?
Yeah.
So that is why this essentially represents set of all triangles in n-dimensional triangles in X in that way. Although the correct word I should say is embedding. Do you
Okay.
understand?
Yeah.
Yeah. So this is how I define Cn of X. Now, of course, there is a natural map though, right? Because how did we define this set? So we have this set, which I'll call it as M, let's say Mn. So we have a set, we have an inclusion map I from Mn to Cn of X, and then we can go Cn minus 1 of X. How do you define that? So Mn goes to each element of Mn, so sigma goes to dou sigma. Oh, right. First, I have to define what dou sigma is. So dou sigma is defined to be, so you have, so what was the map from here? You had a map sigma from delta n to x. I define dou sigma to be equal to the map represented by sigma operated on dou delta n. Did you understand?
Yeah.
So essentially, sigma operated on the boundary. That's all. Right.
Yeah.
Yeah. Sigma operated on the boundary essentially now gives you a map which is from the boundary, right? It's a boundary map. It takes a boundary element and puts it into X. So that is why it becomes an element in Cn minus 1 of X. True? So a
This.
visual analogy. So a visual analogy. If you had a triangle and you mapped it to X, now if you take dou of it, the dou of this map will be the map that maps this triangle to X. But this is the same as mapping this first to X, this second to X, and this third to X. So essentially concatenation of these three maps. I'll write it as delta 1, delta 2, delta 3. So delta 1, delta 2, delta 3 concatenation. So where delta 1, delta 2, and delta 3 essentially belong to Mn minus 1. Mn was defined like this. So this is a boundary map. So it takes in boundary. And if you wanted to represent the boundary map, you can essentially concatenate it, right?
Yes. So basically, I'm taking the element the for delta n. I'm taking the boundary and then taking the boundary, mapping it to X, and mapping the three individual the number of individual boundaries to X. They are equivalent, but then the commutative diagram
Exactly. The commutative diagram.
I cannot understand what are we doing here.
Ha, ha, ha. So then we get a unique map from here, right? This map. Because this is unique, this is also unique. So this has to be unique. This group is well defined. This is a set. This is a free group. So there exists a unique map from here to here, right?
Yeah,
And this is called a boundary map. So this is the boundary map, which I'll denote it as again dou in general. Here we only knew what dou meant for singular sigmas. Now we know what dou means in context of free groups. So similarly, essentially you can define this Cn of x as a map to Cn minus 1 of x, dou map to Cn minus 2 of x, dou map, and then of course it goes on. Now, of course, all of these dou maps are different, right? This is a map from n-dimensional triangles. This is a map from n minus 1 dimensional triangles. So some books write a subscript as well. So here they put n, here they put minus 1. But in general, when you're very suited with the context of how things work, people generally avoid writing the subscript. So this is how it works. So this is essentially what it is. Now you have another relation in front. If you had a triangle and you took its boundary, you get the outside boundary. What is the boundary of this?
if I were to decompose it like taking the three sides, then I think the three vertices.
Hey, but if you had to visually say what the boundary of this is, won't you say there exists no boundaries? Like it is boundaryless? Essentially, if you had to say, let's take this. So let's suppose this was the case and then you assign this orientation. If you took boundary of this, you will get this. But now if you take boundary of this, the boundary of this is going to be in some sense 1 to 2. Boundary of this is going to be 2 to 3. So if I had to attach from where to where it goes, it would have been minus 1 to 2, minus 2 to 3, minus 3 to 1, right? Where the
Yeah,
negatives denote the direction. But if I add them up, this gives you 0, right?
yes,
So essentially this figure in fact has no boundary. So the boundary of something that has no boundary is 0. In our context, it will be E. E is the identity. E is the identity of this group, this C of n. Because you need to give a value to boundaryless figure, right? So that value you give under the equivalence class to be equal to 0 or E. So many books, and I in fact prefer the symbol 0, but you can write E as well. Did you understand?
yeah,
Yeah. So essentially, so these are called closed delta complices. So essentially, M belonging to Cn of x is said to be closed if del M is equal to 0. But there is another thing. If there exists, so another thing, I took del 2 times, right? So this also implies del composed with del gives you 0. True? Boundary of a boundary is 0. Do you understand?
Could you please say this once more?
So if you take boundary first, and then you take boundary of the boundary itself, it gives you zero.
Does this happen for all cases? Because I mean,
Yeah.
the-
So does it happen or not in general for delta n that you try to mathematically write that? Because figuratively I can only give for delta 2, right? So, sorry, delta 3, right? Sorry, delta 2. Because I can't show what R4 matrix looks like. But if you had to visually see it, intuition of it, the boundary of a so boundary is going to be a closed figure. And if you have a closed figure, can you find a boundary of that? No, right? Because it is closed by definition. You made it. So if you had a line segment, the boundary is going to be the endpoints. But what is the boundary of an endpoint? It has no boundary, right?
yeah. So okay,
So in
okay.
that essence only, in general as well, the concept goes. But in that case, you have to mathematically see how the boundary works. But it's an easy thing. By the way. It's why intuition is, in fact, enough for this part. So does this being closed imply there exists an alpha belonging to Cn minus 1 of x such that del alpha equals m? So if del m is 0, does that imply it is in fact the boundary of something else? What do you think? Do you understand the question?
Yeah, I don't think it is necessary, or would I need some
Yeah.
time? Fine.
So you are true, it's not necessary, but can you give me an example, maybe?
Yeah, I'm trying to think of one good example.
Hmm. Well, think of it geometrically only. Maybe take R2 with no origin. Like at the origin, you have a hole. So if you consider C2 of x and you consider this C1 of x, this thing belongs to C1 of x, right? This triangle.
Yeah,
This triangle belongs to C1 of x. And if you consider this to be M, del M is equal to 0, of course, because it's a triangle, closed triangle. But you can't fill this triangle up, right? You can never fill this triangle up. There is a hole.
yes, yeah,
So there exists no alpha such that del alpha equals M. So you can have this condition where even though a triangle, a delta n is closed, but there exists no bigger delta n to cover it. So in the sense, alpha becomes a cover of M. Alpha becomes a filling of M. So when this in fact happens, then M is called to be exact. So this is how exactness works. This is how exactness is defined. So now we can define what homology is and give into what exactly homology means. So the nth homology of X is defined to be the kernel of the del map So I'll define it here first. So first I'll do the maps. Cn minus 1 of x to Cn of x to Cn plus 1 of x. You have a die map, you have a die map. And for the reasons that I will tell just in a moment, I'll put these symbols. Cn, n plus 1, the n plus 1. It's defined to be kernel of dou n quotiented with image of dou n minus 1. Do you understand?
I'm not sure about this the
So,
definition.
yeah, so it is obvious, right, that the image of dou n minus 1 will be contained inside kernel of dou n because of this rule. This is true, right?
Yeah,
So this is obvious. Of course, now this part that it is a normal subgroup or not, that I will not go into proving because that requires a bit more, doing some algebra. But the point is, for the moment, just believe this fact. It is in fact a normal subgroup. But the point of the matter is, or rather, actually, I can make things easier. So I made a too general of a definition. Make this an abelian free group. So what is an abelian free group? This is just on a bit of an extra information. You go into the definition of free groups, but here you had a condition, right? That A1, A2 is not equal to A2, A1. You remove that condition. You put under this equivalence class, in this equivalence class, where is it? In this equivalence class, you put a third condition. This is an extra condition. So for abelianization, A1, A2 equals AI, AJ equals AJ, AI. So once you get this, the free group formed is called a free abelian group. Is that clear?
yeah,
Yeah. So once you have this free abelian group, you can define this thing. And now you have the normality condition because right, if you have a subgroup of a abelian group, it's always going to be normal because what are abelian groups? If you take G and this image G inverse, this is going to give the same as GG inverse image because of abelianization. And then this is just E. And hence it's trivially abelian. Sorry, trivially normal. And hence because it's trivially normal, I can take this quotient. Did you get it?
yeah.
Yeah. So once you can take this quotient, this is how you define what the homology is. Now we'll get into what the intuition of this homology means. So the nth homology, if you consider, it essentially tells you how many n-dimensional holes it has, or rather, how many n-dimensional holes it has. What do I mean by that? In case of, let's say, R2, if you consider, you had this one triangle, right? That was making a problem. True?
Yeah,
So if you had this one triangle that was making a problem, that would imply there exists at least two elements. So the cardinality of H, this will be dou n. So it would be H2 H2 of R minus 0, comma 0. So this will at least be greater than or equal to 2. Because one, you have the trivial element. Obviously, if you take a triangle here, you have a closed triangle before that. So hence, there exists at least two elements. One is this generated by this, and the other is generated by these kind of elements. True?
Yes.
But then, if you see it clearly, those are the only two triangles possible, right? If you take a triangle here, this is essentially the same as this up to translation and scaling.
Yeah.
And if you take a triangle here, these two are the same up to translation and scaling again. Hence, it is in fact equal to 2. So H2 of R2 minus 0 in fact has cardinality equal to 2, which essentially shows you that the number of holes it has is equal to 1. That is this one hole. So
So
essentially yeah,
in that originally you took that the hole was in the origin, but if I consider the hole to be at a separate point, which is not at the origin, I can show that the two triangles are equivalent subject to scaling and translation.
exactly. If you had taken another R2 minus another point, let's say a separate point P, this is the same as this, right? It's homeomorphic. So yeah, this is in fact another theorem. If you have two spaces, topological spaces which are homeomorphic, now I didn't want to go into topology, but if you remember the cup and donut analogy, in that way, if you have two spaces which can be molded into each other, their homologies are in fact preserved. This is group homomorphism. These two groups are in fact isomorphic. There is a separate theorem in what is it called? Algebraic topology. Do you understand?
Yeah.
Yeah. So essentially, yeah, this is the biggest uh, application of free group in math I've ever seen till now, because this is very much used in data science, because you have what is called topological embedding of data. So essentially, you consider data points, and inside that R and space, you somehow prove, or rather, it's a hypothesis. You try to hypothesize that this in fact lays in a lower dimensional manifold, as they say. I don't want to get into what the definition of a manifold is, but if you have to think about it, let's say there was data in R3, and you could actually embed it in a plane which looks like this. Right? Like it's embedded on a sheet. So if you could define such a surface is called a manifold. Of course, the definition is more general, but for simplicity, this is a manifold. And then you essentially go into looking at how these data points are distributed on this surface. And for that, you can actually use homology, because let's say if you had a hole here or a hole here, you can think about the probability distribution. What is data science? It deals with probabilities of finding data at any point, right? So you can think about the probability of finding a point near these holes. And once you have that, you can actually see where exactly these points are in fact clustered around, which is another thing that is dealt with, because when you have a cluster of points, you can be sure that, okay, there is a higher probability of finding points with similar characteristic near those areas. So homology is particularly used in the field of data science nowadays, in topological data science, And then, in fact, there is something called, uh, what is it called? Type theory, which is used in lean programming. If you know what lean is, it is essentially trying to automate math. If you give a proof to in the lean language, the lean checker actually tells you if the proof is right or not. It won't tell you if at any point it went wrong. It won't correct you in the sense it won't give you the right proof. That is what people are trying for right now. They are trying to make an AI out of it. But the point is, lean nowadays they have actually tried to apply a version of type. So lean uses what is called type theory in math. So people nowadays, in fact, use something called homological type theory to do lean. So they use homologies defined on types. So you can think of types as a topological set maybe, and then try to make homologies on it and use it to develop the language further. So yeah, these are some of the contemporary stuff that are being done in group theory. Most of applications of so pure group theory, I'm not sure there are a lot of people that are working on it, but I know a few who are like very pure algebraists who work in pure group theory, but they also very much work with it, anything maybe finite groups. Very few work with these infinite groups. So because Hodge programming is one that is still there for finite groups. For infinite groups, there are not exactly a lot of programs as such. But the point is, a very eminent field in math is these. You know, there are open questions of homologies of a sphere itself, like not S2, not the two-dimensional sphere, but like n-dimensional spheres. In general, what the homology of n-dimensional sphere is, and all those things were actually not clear until like very recently, which is like when I say recently, it's like 1 century ago. Because there is a very nice theorem. Now I won't get into the details of it, where it's like if you can cut a space into simple complex. So example, if I can cut this a sheet of paper into simple delta complexes. So this is two delta complexes, right? Delta two, delta two. Then the homology of this space X is essentially the free group generated by the del operated on these particular delta 2s. This was a groundbreaking theorem. So I'll write it as delta 2 1, delta 2 2. So this was a groundbreaking theorem. I don't remember the theorem's name, but yeah, this is essentially how the theorem worked. And there are further uh, big theorems in homology that can be used to find. So Sn was one such shape that was solved using this. But there are other theorems that can be, so there is something called some Klein, if you know what Klein bottle is, so that same Klein. So something Klein theorem, which goes into defining how if you can cut one space, let's say a sheet into two non-disjoint but a little bit connected spaces, you can define a surjective map from one homology group into the free product of the homology groups. Now, what do I mean by free product is a separate thing. You can again define free product in a similar way to free group. I won't get into the definitions. But the point of the matter is, this is how actual contemporary group theory works in. It's either dealing with finite groups or dealing with these kind of homological groups nowadays. But other than that, many people sometimes say that, okay, what if you put something like R infinity and all? I don't consider this to be contemporary group theory because, well, it's not exactly, you don't exactly need the group structure on R infinity for this. It's essentially the use of vector space. What is it called? Vector space properties of it. That's all. So that is why I don't consider this to be a application of group theory, but this to be the major application of it, the homologies. But yeah, are you clear with what the idea of what a homology is?
Yeah, somewhat.
Exactly. So that is what homologies mean and how things work in contemporary group theory. It tells you some bit into how proofs also work in this kind of math because, example, when we had to define something here, you had no idea of how to go through it, right? You could have either defined it through defining this as a theorem to making this as a theorem, or you could have directly first defined what a free group is and made it a universal theorem. So there are two ways of doing that. So in some sense, definitions and theorems are not exactly disjoint in many cases. They might just follow from one another. If you know what, let's say, axiom of choice is, or you will learn in the future, axiom of choice, and there is another thing called well ordering principle, which well ordering principle at first was thought to be an application of axiom of choice, but it turned out to be the same. Essentially, one implies the other. This was proved by someone. So they were like, yeah, definitions and theorems are not exactly always disjoint. Sometimes definition leads to a theorem, and sometimes a theorem leads to a definition. You just need to open your eyes to the possibilities. So, and another thing is to even define something like this, which seems very artificial, to arrive into something that is actually of literal geometric significance was something that was really groundbreaking. So even so, our when we were taught algebraic topology by Professor Hamid Fogadi, even he was like that how he came up with how someone could have come up with such a idea of defining such a free group for a topological space and then making sense out of it. It must have so the person must have had some kind of premonition. I wouldn't say premonition is the right word. The person must have had some kind of idea already onto how it looked like. So we made some kind of guesses onto how they might have come through it with it. So essentially, the same idea. We started with a triangle in R2, and we were like, okay, we wanted to somehow get this idea of a whole clear because in math you can't define what a whole is because the space outside of X doesn't make sense. Your universe is X itself. So what you can rather say is, I can never find the inside of this triangle. But how can I make such a statement more rigorous? I can say, okay, I have an object sigma, that is this triangle outside, and say there exists no filled up triangle M such that sigma equals the boundary of M. But how do I make it even more rigorous? By taking maps of delta n to x. And well, that these step-by-step procedure is probably how the first person, whoever discovered this homology definition, might have arrived through it. But the point of the matter is this is how math works. You have to sometimes define things to even get to the possibility of of actually proving a theorem. So definitions and theorems are not exactly disjoint. Sometimes you need definitions to prove a theorem, and sometimes you need theorems to actually have a definition. So yeah, that is how I suppose our group theory sessions end. We saw some uh, and insights into how exactly contemporary group theory works and what are its major applications as such. And well, yeah, if you have any questions, you can ask.
Yeah, none really right now.
What?
None really right now.
Yeah, so if you don't have any questions, I suppose that would be the end of the session then. If you have any questions, you can always text me on WhatsApp if needed. But yeah, I hope it was useful to you. And well, yeah, you are in first year or the second year or the third
Uh,
year, or I don't
but
know which year.
I'm in first year.
Okay, first year. So you will see group theory in your third year or fifth semester, that is. And in that, you will be covering everything up to your whatever did we did till the third session, and some extra things like what are these called generators, simple groups, although it's not cared about a lot though, which I